Hello again. This is Math 0482, and this is a lecture on equations quadratic in form. Equations in quadratic form are equations with three terms. The term with the highest exponent, called the leading power or leading term, has a power that is a multiple of 2. The middle term has an exponent that is 1/2 the exponent of the leading term, and the third term is a constant. An equation that is quadratic in form can be written in the form AU squared plus BU plus C equals 0, where U represents an algebraic expression. So here are a few examples of such equations. For example, x to the fourth minus 5x squared plus 4, if you do the substitution U equal x squared, can be written U squared minus 5U plus 4 equals 0. X to the sixth plus 7x cubed minus 8 equals 0. Again, if I let U equal x cubed, can be written as U squared plus 7U minus 8 equals 0. X to the 2/3 plus 4x to the 1/3 plus 2 equals 0. If we do the substitution that U is equal to x to the 1/3, can be written as U squared plus 4U plus 2 equals 0. Another example is t plus 2 over t whole squared plus 8 times t plus 2 over t plus 7 equals 0. If we let u equal t plus 2 over t, can be written as u squared plus 8u plus 7 is equal to 0. Two more examples. If we had x minus 3 the square root of x minus 10 equals 0, we could let u equal the square root of x, and we could have this being u squared minus 3u minus 10 is equal to 0. As a final example, consider 3u to the minus, the last example, 3u to the minus 2 plus 7y to the minus 1 minus 6 equals 0. If we let u equal y to the minus 1, this could be written as 3u squared plus 7u minus 6 equal 0. Again, in each case, what we can do is we can solve the equation in U and then reverse the substitution to find the solution. In each example, doubling the exponent of the middle term equals the exponent on the leading term. Let's do an example. Let's consider x squared minus 4. Let's consider, I'm changing the example, x to the fourth minus 4x squared minus 32 equals 0. If we let u equal x squared, then u squared equals x squared whole squared equal x to the fourth. And we can write x to the fourth minus 4x squared minus 32 equal u squared minus 4u minus 32 equal to 0. Now this one will factor into u minus 8 times u plus 4 equals 0. So u is equal to 8, or u is equal to minus 4. But since u equals x squared, we can substitute back and solve for x. So if u equals 8, then x squared is equal to 8. X is equal to plus or minus the square root of 8. And when we simplify that radical, we get x is equal to plus or minus 2 root 2. Now, when we look at u equal minus 4, that says that x is equal to plus or minus the square root of minus 4. So x is equal to plus or minus 2i. So you see we get two real and two complex solutions. But that was a good example of a u substitution problem and can be used to solve any equations that are quadratic in form. Let's look at another example. Let's consider x plus 2 whole squared plus 11 times x plus 2 minus 12 equal to 0. Well, let's let u equal x plus 2. This turns it into u squared plus 11u minus 12 equals 0. This factors into u plus 12 times u minus 1 equals 0. And so u is then equal to u plus 12 is equal to 0, u is minus 12, or u minus 1 is equal to 0, which says u is equal to 1. But then we replace u with the original expression in x. So x plus 2 is minus 12, x is minus 14, and x plus 2 equal 1, and that tells us that x is equal to minus 1. Neither the original problem nor the solution process impose any restrictions to x, so the solution set for this problem is minus 14, comma, minus 1. Let's consider another example. So consider solving x minus 2, the square root of x, minus 8 is equal to 0. Now, if we let u equal the square root of x, then u squared is equal to the square root of x whole squared equals x. So we can write the original equation x minus 2 square root of x minus 8 equals 0 as u squared minus 2u minus 8 equals 0. Well, this then can factor into u minus 4 times u plus 2 equals 0. So u is equal to 4 or u is equal to minus 2. But then if we substitute back u equal the square root of x and solve for x, we find the square root of x is equal to 4. That means x is equal to 16. Or the square root of x is equal to minus 2. If we square that, we will get x is equal to 4. Now, the original problem imposes the restriction that x is bigger than or equal to 0 because we don't want to have a non-real. Since we have x being equal to 0, that squaring both sides introduced the minus 2. And so that was an extraneous solution. Since x equals 4 is extraneous, there's only one solution, x equals 16. So the solution state is x equals 16. Let's consider another example that has a rational exponent. So suppose we wanted to solve x to the 2/3 minus 3x to the 1/3 minus 10 equals 0. Here, if we let u equal x to the 1/3, then u squared would be equal to x to the 1/3 whole squared, which is x to the 2/3. And so then we can write the original equation was x to the 2/3 minus 3 x to the 1/3 minus 10 equals 0, can be written as u squared minus 3u minus 10 equal to 0, which can be solved by factoring, and we get u is equal to 5, or u is equal to minus 2. But then we substitute back u equal x to the 1/3. So x to the 1/3 equal 5. That means x is going to be, we cube both sides, x is equal to 125. Or x to the 1/3 is minus 2. We cube both sides and we get x is minus 8. So there are two solutions here. It is minus 8 and 125. Let's consider another example, solving 3y to the minus 2 plus 7y to the minus 1 minus 6 is equal to 0. Now here we're going to let u equal y to the minus 1. So u squared is going to be y to the minus 1 whole squared, or y to the minus 2. So we can convert the original equation, 3y to the minus 2 plus 7y to the minus 1 minus 6 equals 0, into 3u squared plus 7u minus 6 is equal to 0. And I can factor that into 3u minus 2 times u plus 3 equals 0. So u is equal to 2/3, or u is equal to minus 3. Now, when we substitute back u equal y to the minus 1 and solve for y, we find y to the minus 1 equal 2/3. So y is equal to 3 over 2, or y to the minus 1 is equal to minus 3. So y would be equal to, in this case, to minus 1/3. So the solution set for y is minus 1/3, comma, 3/2. Let's do another example. In this one, we're going to solve parentheses t plus 2 whole squared. Solve t plus 2 over t squared plus 8, this is t plus 2 over t to the 1 power, plus 7 equals 0. So if we let u equal t plus 2 over t, then u squared is t plus 2 over t whole squared. So we can write our original equation as, using that substitution, u squared plus 8u plus 7 equals 0. And this factors into u plus 1 times u plus 7. So u equal minus 1, or u equal minus 7. But now we substitute u equal t plus 2 over t and solve for t. So setting t plus 2 over t equal minus 1, we find that t is minus 1. When we set t plus 2 over t equal minus 7, we find t is equal to minus 1/4. The domain restriction only says that we have to have t not equal to 0, so both solutions work, and the solution set is minus 1 comma minus 1/4. Here's another problem. Let's consider we have the square root of x plus 10 over x minus 6, that's all under square root, plus the square root of x minus 6 over x plus 10 minus 34 over 15 is equal to 0. Now in this case, what we will get is that if we let u equal the square root of the whole of x plus 10 over x minus 6, then 1 over u is the square root of x minus 6 divided by x plus 10. And so our original equation can be written as u plus 1 over u minus 34 over 15. So if we multiply all the way through by 15u, that changes that equation into 15u squared minus 34u plus 15 is equal to 0. This can be factored into 3u minus 5 times 5u minus 3 equals 0. So u is 5 over 3, or u is 3 over 5. But then we have to do the back substitution. So now we're setting the square root of x plus 10 over x minus 6 equal 5 over 3. We square both sides to get x plus 10 over x minus 6 is 25 over 9. And we solve this and we find that x is 15. Or if we set the square root of x plus 10 minus 6 is equal to 3 over 5, we square both sides, we get x plus 10 over x minus 6 equal 9 over 25. Cross multiplying gives us 25x plus 250 is equal to 9x minus 54, or x is equal to minus 19. And so if we check, we find that both solutions work. So our solution set is 15 comma minus 19. Finally, we return to our original thing of u equaling x squared. So we're going to solve x to the fourth minus 10x squared plus 23 is equal to 0. So here we're going to let u equal x squared, because u squared is equal to x squared whole squared. That's x to the fourth. So we can write our original equation, x to the fourth minus 10x squared plus 23, as u squared minus 10u plus 23 equal to 0. Now this equation doesn't factor, so we have to use the quadratic formula. Here a is 1, b is minus 10, and c is 23. So u is equal to minus b plus or minus the square root of b squared minus 4ac, all by 2a. So we get that u is equal to 5 plus or minus the square root of 2. But now we're going to substitute back, and so we will find that u equal 5 minus the square root of 2, or u is equal to 5 plus the square root of 2. But that means that x squared is 5 minus the square root of 2, or x squared is equal to 5 plus the square root of 2. And so when I take the square root, I'll find that x is equal to plus or minus the square root of 5 minus the square root of 2, or is equal to plus or minus 5 plus the square root of 2. So there are 4 solutions, and you could plug these into a calculator and find out that x could be minus 2.53, or could be plus 2.53 approximately.